तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We were discussing the gas-gas heterojunction with one side very heavily doped, 10^18 or above. In fact, we will see what is the upper limit on this later on when we make the FET, and this is undoped, means not intentionally doped, 10^13 per centimeter cube p type. What I am trying to point out is, just like in the regular n plus p junction, there is a depletion layer here, and as a result you have got the conduction band edge going up like this. This is across the depletion layer, and then there is a notch which we have discussed already, discontinuity in the conduction band equal to delta E c, then is band bending up to the edge of the depletion layer. What I am trying to point out here is, if this were a homojunction or if the notch were not present here, the built-in potential across the junction, thermal equilibrium condition, is VBI, which actually is given by this formula, Vt log Nd by Ni. If the materials are same and no notch, you would have got Vt log Nd by Ni, that is the difference between the Fermi level and the intrinsic level, and this is the in the P region. Total potential, built-in potential would be equal to Vt logarithm of Nd into Na by Ni squared. So, depending upon relative magnitudes of the doping concentrations, you have the built-in potential. Now, let me go back to this particular diagram which we have put in here with a bit more clarity. So, what happens here is, supposing this notch were not present, the Fermi level here is higher in any case. From here to here, the electron transfer would have taken place, and finally, a potential would have built up there. That is the built-in potential. Let us say take the case where notch is not present. Then the built-in potential that you have got here is VBI, which is Vt logarithm of Nd Na by Ni squared, okay, and the built-in potential builds up till you can see the carrier concentration C I to I there. Okay, it is like the war between the two. So, once these are I to I, that is at the same level, the maximum energy of electrons, no more transaction between net flow of carriers is 0, current is 0, thermal equilibrium situation. So, this band edge keeps on rising here by transfer of electrons from here to here till this is raised up to that. That is the built-in potential. Now, because of the notch, see what we are saying now is, because of this notch, if the built-in potential were same thing, I put the dotted line here. If this is shifted down by delta E c, okay, if this is shifted down by delta E c, this also will be delta E c, because it is the same change that is taking place. So, if the built-in potential were same as that of a homojunction, what would have been the situation? That is the built-in potential VBI of the homojunction, and this would have shifted down. And if this is shifted down, what happens? Supposing this is shifted down here, I am putting dotted line because that is the thing which you would see due to that potential variation equal to VBI. Let me put it here. Now, what is the tip of this electron distribution? The maximum is actually below that. That means, because of this notch, if the built-in potential is same as that of the homojunction, there would have been electrons on this side which is having higher energy than that. It is not enough just the transfer takes place till that voltage Vt log Nd by Na by Ni squared, but more electrons will get transferred till this gets raised up that point. That is, till this level is shifted up. What would you say now to the built-in potential? I hope I will repeat it. So, if the potential variation were same as the without notch, this whole thing would have been shifted down here. That is what you get in a homojunction. But now, if that is the situation, the carrier distribution here, highest energy electrons are lower than the highest energy electrons there. As a result, the electron transfer will still continue beyond that point, beyond that VBA of homojunction. That means, the potential here will go up further. How much should it go? Till the energy is equal to that. That means, it must shift up by an amount which it was shifted down here. That means, the built-in potential in this type of junction will be more than that of the homojunction. That is what I am trying to point out. By an amount equal to the notch is a very key thing. Okay? And that means, from here to here, the potential variation in gallium arsenide will be more than that of the corresponding to the built-in potential. See, for example, if you take n plus p junction, almost all the VBA will be on this side. Potential variation here is very small. You can say VBI is equal to this variation. So, in this case, its surface, the potential variation here is more than what you get here by an amount equal to delta Ec by q. Delta Ec is energy that divided by charge is the potential. So, what we immediately say is the band bending here is more than that in the case of homojunction. In the case of gallium arsenide likely to aluminum gas heterojunction, the band bending is more. Okay. Now, you can see visualize once the band bending is more, what happened to the electron concentration here. If you recall, in the case of MOSFET, if the band bending keeps on increasing, it gets inverted on the surface. Okay. So, in the case of homojunction, you can say that at the junction it is close to the intrinsic point. So, if this were the situation, let us say the intrinsic point is here. Now, if it is shifted up by that, the intrinsic point is somewhere here, because if this potential corresponding to the intrinsic change, potential change, this will be additional potential change which will lead to electron concentration here. It is actually if the in the case of MOSFET, if you recall, a p type material, okay, you have the Fermi level like this. In this case actually okay, and it bends down like this. This is the Fermi level and this is the intrinsic level. More it bends down, more it is towards n type, more okay, electrons will be there. In fact, if you move from here to here under thermal equilibrium conditions, you can plot the whole concentration and electron concentration. How will it be there? This is EC, EF and EV. If it were just bending up to intrinsic point, the electron concentration would not have been much in the regular junction, but here it is bending more than that by an amount equal to delta EC, that is what we are telling. There will be electrons here and concentration here. In the regular PN junction, even if bending is more, they will not be collected, whereas if you go down here, that will contain those electrons, that notch will contain those electrons, okay, because of the extra band bending. Now, going back to the diagram once more, if you plot the whole concentration and electron concentration here, how is that? It is p type, I will put it as intrinsic, okay, and it becomes Pp bar or Pp naught bar for thermal equilibrium value, and you will have Np bar. From here onwards, goes up like that and it goes down like that. Surface concentration is much higher than this is a basic principle of MOSFET. Exactly same thing happens here. How much is the concentration increased here depends upon how much is the potential drop between these two. NP bar into e to the power of phi s by V t is equal to the concentration here. Same way here, electron concentration here will be equal to whatever minority carrier concentration is present here multiplied by the potential change e to the power of phi s by V t. More the bending, more is electron concentration. So, what you are telling is in the case of heterojunction, there will be enough electron concentration here because of extra band bending corresponding to this, and the extra band bending is necessary, so that to bring in thermal equilibrium situation. Okay. This is very important to understand that there is an additional delta E c. Suppose I bring it down here, suppose somehow I push this level down here, how can you do that? The electrons will have to be removed out from there. You have to bias this junction. Okay. If I forward bias this junction, we will recall this when we discuss the HEMT. If I forward bias this diode, what will happen? See, now the potential is plus minus here. If I apply plus here and minus here, okay. If I apply voltage across the device which is plus here and minus here, this potential will be reduced by that amount. If you reduce the potential, what happens to electron concentration? It reduces. So, the key thing is I can have a control over this charge in that notch for a given device. I can control it by applying a bias to the junction. I forward bias that, the potential barrier reduces, that is potential change in the gallium arsenide reduces, electron concentration reduces. Okay, we will recall this concept later on. I just put this diagram to tell you that the extent of electron concentration here depends upon thermal equilibrium condition, that more this notch, if delta E c is more, that is more, because it will come from here, go up like that. More will be the potential change in the semiconductor, more will be the charge, that is the band bending is more. So, if you want to have a lot of electrons collected there, what you would go is increase the delta E c. How will you increase the delta E c in a all gas system? You will increase the aluminum content. Delta E c is equal to 0.64 times delta E g. Gallium arsenide band gap is fixed 1.43. So, if I want to have delta E g, the difference in band gap to be higher, I must have aluminum content more in the all gas. Okay. Now, we have to see what will be the upper limitation. In fact, you will see that you do not, people never go beyond about 0.3, 0.35 mole fraction, okay, because it introduces some trap levels and deteriorates the performance of the device. So, we will see that little later, but right now we understand that delta E c, try to maximize it, permitted by technology, permitted by other criterions, maximize that, so that electron concentration in the unbiased condition is large. So, this is all what we have said now. I just put it in word here. In heterojunction, additional band bending takes place such that conduction bandage in the neutral region of gallium arsenide is raised by delta E c, raised by delta E c. Okay, so that the net electron flow in thermal equilibrium is 0. Whatever I have said now, I have put it in words here. Therefore, in the heterojunction, the potential phi of s in gallium arsenide, please go back to this board and see the potential phi of s here, the change built in potential there E is actually larger than the built in potential in a homojunction by an amount equal to delta E c by q. So, that is what is put in form of equation here, phi s in hetero is equal to phi s in homo plus delta E c by q. So, you can see I can turn off this carrier concentration to 0 practically by removing that extra band bending, that is by applying a voltage across the junction forward bias equal to delta E c by q if I put the charge is 0. Please remember this when you go back to the HEMT discussion, because you should know how much voltage you must apply to the gate to turn off the device, and there when the junction like this comes, this is the amount of voltage that must come across the junction. So, due to the discontinuity, this is again whatever I explained put in words, delta Ac in the conduction band of L gas and gallium arsenide, the band bending in the undoped gallium arsenide is more than in the homojunction gallium arsenide. That is by this amount. The band bending is more in gallium arsenide, reiterating what I said in a slightly different way. Due to this effect, large concentrations of electrons are present at the gallium arsenide surface adjacent to the L gas, and they remain there. They remain there due to the notch in the conduction band. That is the key thing. Band bending may be there. If I have a homojunction, there also band bending is there, but there is no electrons left there because they will roll down. Here it will remain there because that notch is there. In the case of MOSFET also, if you recall, when the inversion takes place, the electrons remain there in the inversion layer. Why? There is a notch. If you recall that, so MOS, P type if you take Fermi level, intrinsic, plus minus plus minus. This oxide, and of course, this is the metal. Conduction band of oxide, and this is the region where the electrons are, there is notch, exactly similar to this case of HEMT, there is not there. The electron concentration may not be as high as you can get there, but you can go into inversion region here, and they are locked up there because of this barrier. So, same thing is occurring here. In fact, you can see one-to-one correspondence between the MOSFET and the HEMT. Now, where are these electrons located? I will retain this diagram. These electrons are located here in the undoped gallium arsenide region, and they have been supplied from these dopants. All these electrons have come from here, because their donors are here. So, these electrons from here have fallen down here from a higher energy level to that level, and they remain there, because it is like pouring water into a well, it remains there. This is actually a well, it is actually a well you can call, and physics people will call this as a quantum well if you like. So, we will see why you call it as a quantum well, because we will have more to discuss on that. So, electrons from here are transferred on to here. How much they are transferred on here will depend not only upon this, but upon also the dopants. So, you have enough supply of dopants. These electrons are in gallium arsenide region where doping concentration is low. What have we gained out of that? As a result, ionized impurity scattering is virtually absent. As a result, this we have projected earlier this diagram, mobility versus temperature if you take, just on log scale of course, the mobility will keep on increasing due to the, as you keep on increasing temperature due to ionized impurity scattering, because the impurity scattering becomes more and more important when you go to lower temperatures. Why? Because at lower temperatures carrier velocities are small. So, if there is a scattering center here, if the velocity of electrons is large, the effect of this scattering center is not felt, zip, it goes through. So, the scattering effect is less. That is why the mobility scattering effect at higher temperature is not so much seen due to this, because these are charged impurities. What will happen will be, if there is a plus charge, the electron moving in that direction will get reflected in that direction, move direction. So, the path instead of moving in that direction, the drift electron will be diverted like this. That means the change in direction, change in velocity component, that is the scattering effect that is taking place. Okay. It is not so virtually like hitting in that direction and gaining energy back. At lower temperatures, this poor electron which is moving in certain velocity does not have that much energy, that much velocity. So, it actually gets scattered more, reflected more in that. The chance of the scattering is more when you go to lower temperature. That is why at lower temperature the mobility decided by the impurity scattering is lower. Okay. And this is the other one. There are several scattering effects. In fact, you can see 4 or 5 curves, but I have picked up the most dominant ones in order to avoid confusion, because all other things can be clubbed into this one, lattice scattering mobility. So, now here lattice scattering mobility is mobility decreases with increase in temperature. What is it due to? Again, you take the physical example. Okay. You take the physical example where the lattice atom is here and the electron is moving in this direction. So, now the scattering is because when the temperature is there, the lattice atom is vibrating like that. Okay. It is lattice vibration actually scatters these electrons. Higher the temperature, more is the amplitude of vibration and more is the knocking effect on the electrons. So, higher is the temperature, more scattering takes place because more vibration, therefore, mobility is smaller. So, these two physical phenomena lead to a mobility reduction with the temperature. There is nothing that you can do here for a given temperature that is fixed for a given material and for a given particle. And this particular number, this curve, you can delete. You can delete that curve when dopants are 0, no impurities, absolutely pure material. So, then you can delete that. That means, you will be the entire mobility will be covered by this portion. In fact, the entire once they saw that you make a device like this, electrons are in a region where the dopants are low. Okay. So, ionotropic impurity scattering is reduced. How much is ionotropic impurity scattering is reduced depends upon how much is the low doping concentration. Go one thing, other thing is how much is the other impurities. When you grow the material, other impurity concentration also must be reduced. So, over the years, they could improve the mobility of electrons here by getting purer and purer layers grown, epitaxial growth, MOCVD and MBE technique. You have better and better technique, you could go down to 77 degrees Kelvin, get a mobility as high as about 10 to the power 6 centimeter square per volt second. You will not believe it. At 77 degrees centigrade, 10 to the power 6, okay, that sort of velocity you can get. 10 to the power 5, quite comfortable. You can get at liquid nitrogen temperature, but at room temperature, you are stuck with this curve. At room temperature, best thing that you can get is the best that is reported for gallium arsenide, that is 8500. The 8500 mobility, 8500 centimeter square per volt second. I must tell the dimensions also, because it is centimeter square per volt second. That is okay for a very pure material. Dopants are small, impurities are absent, but the moment you go to higher doping, like 10 to the power 16, 10 to the power 17, you will have that scattering coming up. So, mobility that they talk of in the case of MESFET, where you talk of doping concentration of 10 to the power 17 is about 5000, 4500, 5000 centimeter square per volt second. You get virtually about close to double mobility at room temperature itself, but further benefits you get, you go down to lower temperatures. Okay, now comes the application of this heterojunction. So, you have actually got, all that you do is make use of this junction, so that you can lock these electrons in that notch, okay, and make use of them for transport. So, in a heterojunction transistor, which you can call it as a high electron mobility transistor, HEMT, that is a Fujitsu, they call this as high electron mobility transistor. In fact, this transistor you can see has got semi insulating gallium arsenide. On the top of that, and this is actually the substrate which holds that active layer, and grow on the top of semi insulating gallium arsenide undoped gallium arsenide, which will be 10 to the power 13 of that order, or even better if you have better way of growing. So, a thin layer that could be just 0.2, 0.3 micron thick, because it's after all to support this notch you provide this gallium arsenide, and on the top of that you put this N plus layer, that is aluminum gallium arsenide. Okay. Depending upon how much is the mole fraction of aluminum here, you will have the notch which we have been talking of. So, if you go from here down here, aluminum gallium arsenide, forget about this, because this is the region, the active region is these two. So, when you go in this direction, energy band diagram is like that. So, you have got the electrons locked up here. Now, it is not enough if you have locked the electrons there, you must be able to use them. Now, use in keeping electrons which are locked up somewhere, you must be able to transport them. How do you transport them? Now, you have got electrons which have got high mobility, put a contact here and put a contact here. If this structure is going like this, put one contact between these 2 points. So, I apply voltage between the two, electrons will be transported like that. If I have source here, drain here, I can transport that. That is what is done here. So, to make a high electron mobility transistor, you create a notch by using L-gas gas structure, put a contact, N plus contact, which will serve as a source, which is in connection with this particular electron gas, if you want to call it, not GAS, gas, real gas. Okay. They call it real gas, in the sense it is a cloud of electrons which is present there, which is just arranged on a 2-dimensional plane. Okay. It is one time in a charge sheet. So, the whole thing is a charge sheet here between these two, and the charge sheet is contacted by this N plus layer and also this N plus layer, which form the source and drain. In the sense, as you remove the electrons from this end, this supplies them. It is like in the case of MOSFET, once you invert by applying voltage to the gate, you transport them, and this can respond quite fast, because they are the majority carriers can be supplying very easily. So, this is the situation where you can get a MOS device which has got high electron mobility. Now, notice there is one more, you can't just have a 2-terminal device which you do not have any control, because if you have just put here between these two, I do not have a gate, what characteristics will you get? Just notice there are two things here. One, due to this layer alone, current transport will be there. Due to that 2-dimensional gas alone, there will be current transport. And if I do not have any control, what will happen? The current will keep on increasing, ultimately it will saturate, decided by velocity saturation. You take any charge sheet, apply voltage between the two, it will ultimately saturate. So, you get a current I versus V in a charge sheet there. Okay. You will get it like that, no control, but you keep on increasing that, ultimately you will get that saturation, that due to velocity saturation. Due to the velocity saturation, you will get that. Now, this is only due to that electrons, high mobility electrons. You call those electrons which are here as high mobility electrons. Okay. But in the structure that we have seen here, okay, in the structure that you see here, not only you have that, you have this region also. You have this aluminum gallium arsenide layer, which is very heavily doped, 10 to the power of 17, 18 maybe. What will be the mobility of that region? Low. So, you have two parallel paths, and this layer thickness you get a charge concentration of about 10 to the power 12 per centimeter square, just like in the case of MOSFET, but maybe a bit higher, 10 to the power 12 electrons per centimeter square you get here. Here you will have large concentration of electrons here, because it's thicker per centimeter square, and this thickness of this layer will be how much? That will be about 60 to 80 angstroms, whereas this layer will be 1000 angstroms of that order. So, on 10 to the power 18 doping. Okay. So, 10 to the power 18 into 1000 angstroms is 0.1 micron, 10 to the power minus 5, 10 to the power 18 into 10 to the power minus 5, 10 to the power 13 per centimeter square, 10 to the power 12 per centimeter square. So, the current will be controlled by the top layer. This is the layer which will control the current. In the sense, entire transport will be controlled by this. So, you will have low mobility effect. So, put a gate here so that you can deplete the entire layer. Okay. I will come back to those more details after. Right now, I will keep you in the perspective how you are avoiding that current transport through that. You have a metal semiconductor rectifying Schottky barrier. So, you can see the Schottky barrier haunts us everywhere now. Okay. In the case of gallium arsenide based technology, you have that metal semiconductor contact, which is rectifying. So, there will be depletion layer across this. More about the impact of that we will see little later, but right now there will be depletion layer width. Now, you can have the depletion layer width chosen, or you can have the thickness of this layer and doping adjusted such that the entire layer is depleted. Entire layer is depleted. If the entire layer is depleted, that is what we plotted. Whole current will be there. It is equivalent of metal oxide semiconductor. Instead of oxide, what you have is a depleted layer, epsilon r larger than the oxide. So, people talk of high dielectric K constant, high K dielectrics for MOS device, because the K for oxide is 4, you will work for 8, 10, 12, 20 K. Here automatically you have got high K, about 12.8. 12.8 is the high K, around that 12.8 to 13, because aluminum gallium arsenide, almost same as gallium arsenide, about factor of 3 more than that of oxide you get here. Okay. So, you get a benefit of that high K, plus your benefit of the metal semiconductor contacts which produce a depletion layer. So, current is flown only through that, plus you can apply voltage between this and this, control the charge here. Okay. Just like in the case of MOSFET. In the case of MOSFET, once it is inverted, you apply voltage between the gate and the source, the charge in the inversion layer gets affected. For example, above the threshold voltage, if you apply VGS, that VGS minus V threshold appears across the oxide, and that changes the charge. Similar thing will happen here. I am not discussing it right now, because I just giving you just the principle. We will go into more of analysis after discussing few aspects. So, okay, that is where the gate plays a role in depleting the whole thing, and also to get a control on the charge here. So, once you get a control on the charge here, you can vary this current. You will have similar curves plotted. Okay. You can get Pg. We will come back to this. Right now, I am just saying that you can get gate control and vary the charge in of this layer and vary the current. There will be few gaps in the understanding right now, but everything will clarify further as we go on. Now, I would like to project some of the names which have been given to this device, because you can get confused with the names. HEMT, high electron mobility transistor, was named as Fujitsu, but this is referred by different names for different organizations, all mean the same thing. So, people ask what is there in the name, it is the same device. Okay. But people like to call MODFET, it is the same high electron mobility transistor, modulation doped field effect transistor. Okay. It is called by University of Illinois, Cornell, Honeywell, industry and the universities. Okay, they have understanding that we will call it as MODFET. MODFET is the same thing, heterojunction field effect transistor. Why do you call MODFET? You dope in a structure, you dope selectively this region you do not dope. See, for example, when you grow, go back to this, start growing gallium arsenide here, no doping, growing gallium arsenide, dope that only. So, you are doping in certain portions of the device. In the previous lecture, we discussed gallium aluminum arsenide, gas, gallium arsenide, etc. One diagram we put where none of them are doped. Another diagram we put all of them are uniformly doped. Another diagram we put where only gas is doped, that is modulation doped. To tell you that only the selected regions are doped, you call it as also selectively doped field effect transistor. Okay. So, now here the modulation doped means actually it is doped in selected regions. Your doping is modulated. How do you modulate? One layer undoped, other layer doped. That is all this done. Then you call it as selectively doped heterojunction transistor by AT&T Bell Lab, and you do not have time to say selectively doped heterojunction transistor, do not have time to say SDHT, you call it as SEDIT. This is pronounced as, that is pronounced as okay, SDHT pronounced as said it. This is the okay, this is the American way of doing things, in the sense shortcut. In fact, when first time when I was talking to some people about this aluminum gallium arsenide and gallium arsenide in a meeting, in the research class meeting, they used to, or the faculty, the research group meeting, somebody started saying gas. So, gas, when somebody says you think it is real gas, but this is shortcuts, gas, indium gallium arsenide, in gas, no outgassing, in gas, like that. Okay. So, this is the terms which are used. Okay. So, selectively doped heterojunction transistor, said it. So, these above two names indicate that only certain region is doped, that is all the meaning, both are heterojunctions. Okay. Other names that are given are two dimensional electron gas FET, TEG FET. This implies that the conduction along the channel occurs in a thin sheet of charge. In fact, your MOSFET also can be called as a TEG FET, but you do not call it TEG FET because for fear of being confused with this heterojunction transistor. Okay. Though it's, I would like to say that it is a heterostructure device, you do not consider it that way, because the oxide is amorphous, it is not single crystal. So, that is a TEG FET, two dimensional gas. Then I see that recently some people also call it as SED FET, selectively doped field effect transistor, same meaning as MODFET. So, it is only a way of addressing it. This is emphasized that the doping occurs in a separate region from the channel. Okay. I just thought I will bring it to your notice that all these mean the same thing, because MODFET is same as HEMT, SEDIT, TEG FET, all. Now, let us take a look at this. I just deliberately put this particular diagram, because whatever you have drawn on the board, which I would be happy to see and be done with that, because after all, as far as the external world is concerned, it is the electron which is locked up there, which you are transporting. How it is locked up, where it is locked up, we may not cover, but how much you can dump there would be controlled by certain factors. For that, we just take a look at it. In fact, we can just borrow the results, quickly go through this. So, here I will just show this here, this particular region. Okay, one more thing that I just did not mention is, just to go back to that, in this structure you bring in more layers. See, what I said is this particular layer is doped very heavily, okay, and you can take out the effect of that by depleting that. But these electrons which are present, they brush aside those dopants. The dopants are just in the close here. So, if I have only gas heavily doped right up to this point, then these electrons which are present are in communication with close contact with the dopants. So, what you do is you terminate a thin layer of 20 angstroms, 20 to 50 angstroms, usually 20 is the one that you put. Why we should restrict to 20 also will be clear when you see the transconductance of these devices. A thin layer you put which is not doped, but aluminum gallium arsenide. You need to put aluminum gallium arsenide only here to get this notch. You need to have aluminum gallium arsenide, but do not dope it just close to this point. Stop the doping on this point. So, you have, strictly speaking, in a high electron mobility transistor, you have semi insulating substrate, undoped gallium arsenide, a thin layer of undoped algas and 0.4 micron layer of algas doped. So, those dopants supply the electrons, the undoped layer here separates the channel from the dopant scattering, impurity scattering. So, that is called a spacer layer or a setback layer. Okay. So, you have one more layer there which are not shown here when you really put it. Okay. So, that is what is shown in that particular diagram for the sake of completeness. That is, you will see here there is a doped layer from up to this point, that is aluminum gallium arsenide. There is a small undoped layer here, aluminum gallium arsenide, same band gap, but dopants are not there. This shows the dopants are stopped there, undoped, and beyond this point undoped gallium arsenide. You get of course the notch here because of the how much is this notch depends upon mole fraction of aluminum gallium arsenide. So, that is there. So, the thin layer you put it here. Now, this particular layer is equivalent of a quantum well that we have been talking of. In the sense, when you confine the electrons within the potential well, okay, if you confine the electrons within a region, I think I have to draw that diagram. Suppose I have a potential well like this, okay, V of x 0 to L, like that. You saw it in the previous lecture. Gas gallium arsenide, if you take, you have the conduction band varying like that. This will be a conduction band of gallium arsenide here, aluminum gallium arsenide, because on the bottom side you will have like this valence band, conduction band. I am not showing the valence band. So, the potential hill is in the conduction band itself. Now, when you have a potential well like this, electrons which are present here cannot occupy any level, because the moment you make that potential well narrower, the energy levels are no longer continuous here. See, when I take a conduction band of a material, the energy levels are continuous because of band splitting, energy levels are continuous. But the moment you confine it like this, okay, the energy levels are no longer continuous. They split up into, if you want to take one electron, that can take only restricted energy levels, the potential well. In fact, the energy levels have been arrived at using a potential well concept itself. So, the whole thing is, I will just go through quickly the analysis, okay, very brief analysis, just a bird's eye view of the potential well. Okay. Just take a look at the well, and if you take a look at this, it is similar to that. We are confining the electrons into a well. The shape of the electron may not be just shape of the well may not be like that. It is a well which is gradually varying. Okay. You get into the well here gradually from this side to that side. You do not jump into the well. Okay. So, this is just on the lighter sense. Okay. So, now you can, what we have shown here is you will have energy level E1, energy level E2. In fact, if there is one electron, you can take this point, it will occupy this or this, and if there are more than one electrons, okay, all of them can occupy this energy level. It is split up into a band. So, you will have sub bands, you will have sub band corresponding to energy E1 and E2. I will just go through that quickly what this implies is for the potential well, without spending too much time. So, donor impurities are in the aluminum gallium arsenide layer and a setback layer I just mentioned, the thin layer 20 to 50 angstrom depending upon application from the interface to reduce the coulombic interaction. I just whatever I explained there I put it here. So, that is the spacer layer which is present between the two layers here, that layer I just, that is the layer explanation I am putting here in the diagram. Depleted region in the aluminum gallium arsenide layer is positively charged and is balanced by the electrons in the gallium arsenide. Whatever plus charge is present here, that is balanced by negative charge in the gallium arsenide, and negative charge comes from where? In two regions are there. One, this gas notch mobile electrons, other one depleted layer, that is there are all these fixed charges are there, and here there are fixed charges are there. So, this is compensated by this charge and also this electrons there. Okay. That is the meaning of that. So, the large electric field present in the gallium arsenide bends, band bending is more. In fact, we have given enough explanation on that. Band bending is more here, therefore, electrons are knocked up there. So, in MOSFET, we will go back to this afterwards. What we are telling is there are two levels there, E1 and E2, which you showed. Let me just go into that. This is the, if there are two energy levels, the E1 levels will be filled first completely. Okay. If you keep on dumping electrons into this notch by increasing the delta EC, you will have electrons rising up to this level also, or by increasing the doping, you may have the electrons going into this region. So, but initially the E1 level is filled up and it breaks up into a band instead of one level. That is what is put here. The second sub level energy E2 is partially filled. See, after all, if there are two levels, okay, a band, one band will get filled completely, then only the next band will get filled up. That is the implication of that. So, now we will go back to this understanding, that is, I have to keep going back. The inset is here. This what it is, we will see later. This is actually a wave function, this is the energy level, E1 and E2, E1 and E2. Let us go and quickly analyze that. In a potential well problem like this, we are viewing this also as a potential well. So, in a potential well problem like this, a particle is located there. Okay. Now, where to find the particle? In x and in energy. Probability of finding, see, you cannot just as let us say with certain momentum the particle will be there. Heisenberg uncertainty principle. You cannot, if there is an uncertainty in delta x, there will be uncertainty in the energy or momentum. So, but whole thing is governed by a probability, where in x and in the momentum space, where can you find these electrons, that is governed by the a probability function psi. Okay. That is the wave function, and the whole probability, the entire probability is controlled by that wave equation, which is called as a Schrodinger equation. I am sure you must have heard it, you must have been hearing it right from your high school days. The Schrodinger wave equation, of course, everybody puts it, accepts it and puts it down. It is derived from the quantum mechanical theory. So, we do not, I know that it takes a lot of effort to go through the thing using the operator principle, etc., but it is accepted thing, so we will just take that. So, the psi variation, okay, it decides a solution for that wave equation will tell you what is the probability. Psi is the probability function, implying psi square modulus integrated over a volume delta V, integrate over the entire volume if you put, that will give the total probability of finding a particle in that volume from minus infinity to plus infinity. What is the total probability of finding a particle in the entire volume? 1. So, psi square dV integrated minus infinity percent into 1. So, psi square modulus is actually the probability of finding the particle in a certain volume there, delta V volume. So, that is all that is there in the Schrodinger equation. You are telling what is the probability. So, psi square is the probability actually, not psi. In fact, psi square modulus I put because psi will be having e to the power j x dependence. Psi into psi star is psi square. Psi star is complex conjugate. Okay. That is the famous Schrodinger equation that we always see. One has to solve this particular equation. So, psi is the probability function, wave function, psi square is the probability of finding the particle in a volume with certain k, m is the mass, Planck's constant, h bar is h by 2 pi, h bar is h by 2 pi, h is Planck's constant, E is energy of the particle as a function of x and momentum. V of x is the potential at that point. For example, if you take this, the V of x, if you take it as 0 here, it is V naught here. That is the height of the potential well, or that is the depth of the potential well is V naught. So, an electron present here sees a potential equal to 0. Here the potential equal to V naught. The simplest solution that you can get is when V naught is infinite. Okay. That is all everybody solves. I also will do that thing quickly, go through the thing. So, when that is V naught is infinite, that is an infinite well. Where do you see this situation? You take a metal where electrons are present. There is a variation in potential within the metal. You come up right up to the boundary of the metal. What is the potential? That the whole thing is a potential hill, potential well, and at the boundary of the metal, a sudden rise in potential, because you must take infinite or large amount of energy to take the electron out of the metal into vacuum. So, this is a picture of the metal actually also, but it is the well, how much well is the wide, it depends upon the metal thickness. Here this well is very narrow. So, what you apply there for the metal, similar thing holds good here in the case of a quantum well. You call it quantum well because the energies cannot take all sorts of values, take only values guided by quantum numbers, n is equal to 1, 2, 3. That is what you get from the solution. So, now let us see, in a couple of minutes we will just go through this quickly. For a particle trapped in the potential well, the energy levels which are permitted to occupy, that is what we are telling. The moment there is a probability here like this, there are discrete energy levels which the electron can take. That is obtained by solving this equation. So, this is what I put here, the potential well V equal 0 here, V equal V naught there. This is the same thing with V naught infinite potential well. Solution is very simple. Okay. Now, you have to modify that solution later on if you want to get for the finite potential level. And if you want to get a solution for this particular thing, the hell will break because it is much more complicated. The potential is varying with x. Okay. So, you have the follow that Schrodinger equation with V of x equal to 0 between this region and V is equal to infinite in both regions. Boundary conditions are potential is infinite. When you say potential is infinite, what is the meaning of that? What is psi there? Probability of occupation in the region where potential is big potential 0. So, you are solving the Schrodinger equation with V equal to 0 here, with the boundary condition psi is equal to 0 here and 0 there. So, from the more complex one dimensional equation, you remove that V, you get this equation. See, just go back here, V is 0 in the region, I get 2m by h bar squared E into psi of x. That is what you get. That is the equation which you solve with the boundary condition psi equal to 0 at x equal to 0 and L. Psi equal to 0 implies means that probability of occupation is 0 there at the boundary. Okay. With that, what is the solution of this equation? And you remember, you have removed the time dependence, only the x dependence. Okay. Because from variable separables you can get them together. So, solution for that is will be some constant into psi k of x plus another constant into cos k of x. That cos term will be 0, because at x equal to 0 psi should be equal to 0. So, psi k of x plus cos k of x, cos k, otherwise x equal to 0 will give 1 cos k of x, probability will not be equal to 0. So, cos term is 0. So, even though it is a second order differential equation, you write only that the cos term plus psi m2 cos term is made 0. So, that is a variation. Now, here psi of x should be equal to 0 at x equal to L, at x equal to L. So, now k will take actually values, k is actually this quantity. Okay. So, k is actually a wave number which is root 2 m e by h bar. So, k of x should be equal to, I think I will not continue on this, all that we have to say is sin k of x should be equal to 0. So, k of x should be equal to 0 for certain values of k. Okay. So, k into L can take values equal to n pi. K into L can take values equal to n pi, n varying from 1 to 3. I will just come back to this again, because so you put k equal to this one and then we will equate it to this particular term. I will go back to this because I will not continue on this now. We will take this, quickly come to this, then go back to HEMT, because that will be continuity.